Section 9.1, we talked about graphing in 3D. So 2 things that I need from you. First, for the 2 skills you need to be able to have, I need you to be able to find each of the intercepts, the x-intercept between setting y equal to 0 and z equal to 0. To find the y-intercept, which is where x equals 0 and z equals 0, and the z-intercept, which is where x equals 0 and y equals 0. You'll then be asked to, or you may be asked to plot points. Connect with line, and shade in the triangle. Okay, this was a question. You can see an example of a question like this on the quiz. I forget which week it is. But if you look through the quizzes I have posted, there's definitely a question on plotting this. So it would say something like, graph the first octant of the plane with blah, blah, blah equation. Okay, so to do that, you would just find all the intercepts, plot those points on your XYZ plane. Again, the one going up is z, the one going out is x, the one going side to side is y, to be clear. The other thing that we need to do is be able to find, or if you're given a function f of x comma y, be able to plug in values like f of 2 comma 3. Okay, I'm not going to do examples of these for the sake of time. I'd rather talk about partial derivatives. Okay. I guess I'll do a quick example. If I give you f equals x squared plus y squared plus 3xy, and I asked you to find f of 1 comma 2, this would be 1 squared plus 2 squared plus 3 times 1 times 2, which is just 1 plus 4 plus 6, which is 11. Okay, something like that. Okay. And then again, for finding your intercepts, if I give you an equation to graph first octant of, let's see, x plus 2y plus 3z equals 6, our x-intercept is going to be x plus 0 equals 6. Our y-intercept is going to be 2y equals 6, so then y equals 3, and our z-intercept would be something like 3z equals 6, so z equals 2. And then I plot my points at 2, 3, 6. Connect them with a triangle. I just need to shade in that triangle. But again, since this is a triangle that's just kind of like sitting on top of this, we played with GeoGebra during this lecture and kind of saw what these planes actually look like when they're all spread out. Okay? But that's all I would expect you to do. All right, moving on to section 9.2, partial derivatives. So 9.2, partial derivatives. Here, we saw that we had this term with respect to. Okay. So I always abbreviate this WRT. So for example, so with respect to means treat this as a variable, and let's say all else, like a constant. Okay. So, for example, or more specifically with respect to x means x is going to be treated as a variable. So treat x as variable. Treat y as constant. And then, of course, we're going to differentiate. And then with respect to y, again, means treat y as variable and x as our constant. Okay. And then we saw that we could do some higher order things. So I guess a quick example of this would be if I had some function f of x comma y. Notice this notation clues us into the fact that we're in 9.2. I have f of x comma y. Let's say that I have this equals x cubed y plus 3x y squared plus y to the 5th, or something like that, plus 13. Why not? Here, the derivative with respect to x is just going to be 3x squared y plus 3 y squared plus 0 plus 0. Okay, again, notice, I took the derivative of this guy, 3x squared. Y is just a constant, so it's just along for the ride. The derivative of 3x, that x goes away, it goes down to 1, so I just have 3 times y squared. That y squared, again, is just left over from up here. And since both of these are constants, their derivatives are 0. Similarly, f sub y is going to be x cubed plus 6xy plus 5y to the 4th, and again, plus 0 for this 13. Okay, we saw that we could do this with higher order partials, or second order partials is really what we care about. Second order partials. And my favorite way to do this was with the tree. We had our f. Down to the left, we have this. This was always with respect to x. So you got f sub x. Here was always with respect to y. I got f sub y. And then down here I got f sub xx. Again, this was with respect to x. I got f sub x y. F sub y x. This was with respect to x. F sub y y. So these were all of my second order partial derivatives. And we know that these two are equal in the middle. So it was kind of a good way to check if we had done things correctly. Was if these two weren't equal, we know that we had done something wrong. Okay. So yeah, I will let you guys look at the exam 3 review solutions for an example of this specific problem type, because you'll see in a second that I have to do one of these for exam 3 as well. All right. Then we have 9.3 was our last section that we talked about on Tuesday, or on Thursday of last week rather. So this was maxes and mins in 3 dimensions. So here we have a process. Step 1, we're going to find our critical points. The way that we do that is we, first off, so I guess let's actually do this slightly differently. We're going to find so for 9.3, these maxes and mins. Step 1, we're going to find all of our partial derivatives. I want to go up to the second order to be clear. Step 2, I'm going to find my critical points. I did this slightly differently in the notes that are posted, hopefully momentarily, online. So find our critical points. We're going to set f sub x equal to 0 and f sub y equal to 0. And then we're going to solve the system of equations that we get. To find some points. A comma B. Okay. Now, step 3, we are going to make a chart where I have my points, A comma B, and then I'm going to just plug them in, fxx, fxy, fyy, and then we had our discriminant, d, which equals fxx, fyy, minus fxy squared. So this is an equation. And then here what I mean is we're going to plug in our point, and then we're going to take all of these values on the left and plug them into our discriminant over here. Okay? And we said that making a chart like this was a really nice way to keep track of our points, especially when we have multiple points going on. And then step 4, we're going to classify our critical points. Okay, so classifying our critical points, let's get another chart going. I love charts, you know. So if I have d greater than 0 and fxx greater than 0, these are the same, which makes me happy, so I have a min. If d is greater than 0 and fxx is less than 0, differences make me sad. So they have a max. And then if I have d less than 0, I don't care about fxx, I have a saddle point. And then if d equals 0, then we don't know. It's inconclusive. All right, so that was how we would classify those things. Again, I wrote up those steps a little bit differently in the review that I've posted, but let's go through and do an example of this, because I think that an example is pretty helpful. So I had written step 3 in a couple of steps, or the problems for 9.3 I wrote in a couple of steps. I'm just going to do them all in one fell swoop. Okay, let me look to see which one of these would be a good problem. So problem number 2 I've noted in the solutions is easier than the one on the exam, so let's do problem number 1. For, again, all of these are coming from the exam 3 review worksheet. So I have f of x comma y equals x squared plus 4y squared minus 2 x squared y plus 4. Okay, So the first thing I want to do is I want to find all of my partial derivatives. Let me know what my margins are so I can kind of try to center myself. So I have my function f, I'm not going to rewrite it. F sub x is going to be 2x minus 4xy, and f sub y is going to be 8y minus 2x squared. Again, this is 4xy. While I'm at it taking some partial derivatives, I'll find fxx equals 2 minus 4y, fxy equals negative 4x, which is again equal to fyx, and fyy is going to equal 8. Okay, so I found all of my partial derivatives. Hooray. Now I want to find the critical points. So part 2. We're going to find our critical points. What I mean to say is we're going to set 2x minus 4xy equal to 0 and 8y minus 2x squared equal to 0 and solve. Now, there's not necessarily an easy way to do all of this, but we know that both of these guys need to equal 0. Okay, all right, so